exponential growth and decay is an application of logarithms and exponential functions, logarithmic and exponential functions. Really, I mean, look at the formula here, it's exponential, right? But you know now that sometimes we use logarithms to solve exponential equations, and so that's how it fits in with the logarithm part. And exponential growth or decay is something that you see often in the real world. And so for things like population growth or investments or loans, so you see it in the finances, in population growths, radioactive decay that you've probably learned about in chemistry. Those are just some of the applications, but you'll see more kind of as you go through some examples. I'm only going to do 2 examples with you, and then I'm just going to get you trying some, and I'll give you a chance to try some, and then we'll go over them if we need to and whatever. But this is the formula. It's on your formula sheet. This part of it is on your formula sheet. This stuff is not. So this stuff down here you need to know. It's going to give you y equals ab to the power of t over p. You need to know how to use that. So when we're talking about something that's growing exponentially or decaying exponentially, which is basically increasing or decreasing, decay just means a decrease, y is equal to the final amount. At the end of the time period that you're considering, y is the final amount. A is the initial amount that you started with. So if you're talking about bacteria culture and how it's growing, which does follow an exponential growth, A would be the number of bacteria that you started with, Y would be the number that you end it with. And then we have B, which is the growth or decay rate. How quickly is it growing or decaying? In terms of either a percentage or a number, like we often say like doubling or tripling, that kind of number, that would be the rate. T is the elapsed time, so how long are you looking at this particular population or whatever it is, and then P is the growth or decay period. How long does it take for that growth or decay rate to happen? So if it's doubling and it takes 3 hours to double, P would be 3 and B would be 2. A 90 milligram sample of a radioactive isotope has a half-life of 5 years. Do you know what that means? Yeah? Can somebody explain it? No?
Isn't it like every 5 years the life of it goes in half, right?
The size of it, right? So it's a sample of radioactive material and it's decaying, and every 5 years it's down to half its size. So your chemistry teacher can explain that more, but every year it goes down to half the size. How long is it going to take until there's none left? Never. There's never going to be none left, right? Trick question. But you got it. And if you think about it in mathematical terms, and even as a function, an exponential function has that horizontal asymptote at 0, because it's never going to actually reach 0, right? That radioactive sample is going to get so small that like you couldn't see it even with a microscope, but it's still going to exist. It's never going to get down to 0. So this asks us to write a function m of t that relates the mass of the sample m to the elapsed time t. So it's going to be something like what we saw there on the other page. Y equals ab to the power of t over p, where y we're actually going to call m of t. What's a? 90, it's the initial amount. What's b? B is the decay rate. So it would be 1/2. It's going down to half its size. T is just going to be T, because we're just writing the function. And then P, that's the 5 years. It doesn't matter what units you use for these things. Like, it doesn't matter if we're measuring in milligrams or grams or kilograms or whatever, as long as both A and Y are measured in the same units, and both T and P have to be measured in the same units. So here we're measuring time in years. P is in years, so time is going to be in years. So the function is just going to look like this. Now that we have everything, we can just write it. M of T equals 90 times 1/2 to the power of T over 5. That's the function. Then we can use that to answer some questions like in B and C. What will the mass of the sample, that should say B, in 6 months? So now we have a value for T. What's the value of T? 0.5, right, half a year. Remember we said time is measured in years. So half a year, that's 6 months. So we're going to do M of 0.5. 90 times 1/2 to the power of 0.5 over 5. And then we can just use a calculator to evaluate that. And we end up with 83, well, I'm going to call it 84 milligrams. It's 83.97. The next part of the question asks, how long will it take for the sample to have a mass of 0.1 milligrams? Which variable is that 0.1?
MT.
That's M of T, right. And it's measured in milligrams. The A is measured in milligrams, so we don't have to worry about units and switching anything. We can just fill it in. We're going to go 0.1 equals 90 times 1/2 to the power of T is what we're trying to find, right? How long will it take? T over 5. I'm going to show you how you can solve this algebraically, although I think you could already do it. But you could also solve it graphically. I'll show you that too. But to solve it algebraically, I'm going to divide both sides by 90. And then, because we're trying to solve an exponential equation, we could either get a common base, which I don't think is going to happen, or we could use logs. So I'm going to take logs of both sides. And then once I do that, this exponent can come down as a coefficient. So it would be log of 0.1 over 90 equals T over 5 log 1/2. I'm going to divide by 1/2. And then that'll give me what T over 5 is. And I just want to, let's see, T is going to be equal to, I'll have to multiply by 5. 5 log 0.1 over 90 divided by log 1/2. Then this I can just put into my calculator. 5 log 0.1 divided by 90 divided by log 1/2. And I get T equals 49.07 years. How long will it take the sample to have a mass of 0.1 milligrams, 49.07 years. If you were to graph that m of t equals 90 times 1/2 to the t over 5, you'll just put in a y and an x instead of m and t. Graph it, and then on your calculator for b, you could just go second trace value 0.5, and it'll give you the 84. And for the other one, you'd have to also graph y equals 0.1 and find where those two intersect, and that'll give you the 49.07 years. Here's the next problem. A city with a population of 800,000 is projected to grow at an annual rate of 1.3%. Estimates the population of the city in 5 years. It's called an estimation not because we're guessing, but because it's not a sure thing, right? Like, it's projected that it will grow at an annual rate of 1.3 years, but no 1.3% per year, but nobody knows for sure that that's exactly what will happen. That's why it's called estimate, not because I want you to guess at your answer. We're actually going to calculate the answer, but it's an estimate because nobody can actually see into the future and know for sure that that's exactly what's going to happen. What's the question mark here? What are we trying to find? Y, A, B, T, or P? Y. I'm going to put a question mark there. That's what we're trying to find. So the other ones we should be able to fill in. What's A? 800,000. What's T? 5. Because it asks estimate the population of the city in 5 years. What's P? P is 1 because it's 1 year. B is the tricky one. What is B for this one? 1.3%. It comes from the 1.3%. But percents we always write as decimals when we're calculating with them, right? So what's 1.3% as a decimal? 0.013, right. So we're going to use that. But if I make B 0.013, that's a number less than 1. Then it's decaying, right? Or decreasing. But we want this population to grow. Add that to 1, right. So the growth rate here is 1.013. Anytime that you're working with percentages, you're going to have to either add or subtract from 1. So if it's growing, you add the percent to 1. And it's basically, when you say 1.013, it means it's keeping the 100% that it already had and adding 1.3%. So that's the 1. The 1's the 100% of the population that's already there, and then you're adding to that. Now we should be able to figure out the answer of what the population will be in 5 years. It's 800,000 times 1.013 to the power of 5 over 1. And I get 853,370. I'm going to round to a whole number, right? Because we're talking about the number of people in a city. You need to round it to a whole number. We're not going to have a fraction of a person. So the population in 5 years should be 853,370. Then how many years will it take for the population to double? Now we're trying to find T. And what is your Y value? 1,600,000, right? Because it's double the 800,000. So I'm just gonna do that. Put the 1.6 million in for y and leave the t as a t because that's what we're solving for. Divide by 800,000, so you get 2 is equal to 1.013 to the power of t. And then either take logs of both sides like we did in the last one, or could we just switch this one into exponential form? It would be log base 1.013 of 2 is equal to t. Or you could take logs of both sides and you'd get, once you isolate the t, log 2 divided by log 1.013. Either way is good. I just wanted to show you both. And you end up with 53.7 years. Do you think that's realistic? Will the population of that city double in 53.7 years? Probably not, right? Like the population of a city is not going to stay at the same annual rate of growth for for 50 some years, right? Things change. So maybe when you're looking at this kind of problem, maybe, the first question is reasonable. 5 years, it might keep a similar growth rate. That's not going to keep a similar growth rate for 50 some years.